We are live. You just don't exist. You exist.
All right. It's going to automatically follow. Perfect.
Apparently you live in the top right, top left. We'll just go.
Okay. All right. Hello, hackers. Welcome to CSE598, Advanced Vulnerability Research. It's actually Applied Vulnerability Research. Typo on the slide. All right, we're off to a good start. This iteration of AVR is focusing on XNU. It's the basically base of all of Apple's various operating systems. We're going to have a lot of fun stuff, fun times doing some crazy stuff in kind of Mac OS underpinning land. First things first, I'm Adam Dupay. I am an associate professor here at ASU in cybersecurity. Just some quick introductions. You might have heard from other upstart professors here that they think they're cooler than Adam Dupay. No one is cooler than Adam Dupay. I want to say that right now, especially for the people watching on Twitch. As Adam Dupay, I've competed on Team Shellfish in the World Championships of Hacking, and then went on to co-found the Order of the Overflow. We ran the World Championship of Hacking with a new friend of mine, Zardas. We created the CTF Radio. I don't know if you guys are into podcasts, but I highly recommend CTF Radio. It's a really cool podcast. I am one of the core people behind Pwn.college, and recently became the Dean of Binary Exploitation of something called DEF CON Academy. Tell all your friends, Adam Dupay, best cybersecurity professor at ASU. All right, got that out of the way. Who here, big fan of Adam Dupay? Yeah, all right. We have Twitch action? People are fans of Adam Dupay? We can wait a little bit for some Twitch love. Yes? All right, good. We got Twitch love. All right, perfect. Adam Dupay, best and coolest cybersecurity professor at ASU. All right, anyways, moving on. What is this course? Well, I just said basically already, so we're already going off the rails. CSE598. This is a graduate level course on applied and advanced vulnerability research techniques. If I could, I would have named it AAVR. And the camera lost me. All right, too cool for the camera. All right, so again, the last iteration of applied vulnerability research, we went in and focused on finding bugs in real programs. We had a large amount of real programs that we were finding and exploiting bugs in. This iteration, we're ramping things up to 11. The only thing we're going to be looking at is real software underpinning your wait, that's not a MacBook. All right, who here runs Apple products in any capacity? All right, like 4 people in the class. Okay, perfect. Yeah. Well, us too, you see, we tried Linux. Adam Dupay, big fan of Linux. Unfortunately, it didn't work. So anyways, all right. So goal of this course. All right, who is familiar with Pwn.college? Excellent. Okay, so Pwn.college, cool platform. It takes you from 0 to almost hero, right? You start out not necessarily knowing anything, and by the time that you've gone through the platform, you know a lot of building blocks of these cybersecurity skills. You know how to exploit a kernel. You know how ROP works. You know how to reverse engineer software. You know how to spot different types of bugs, et cetera, et cetera, et cetera. But putting that all together on a real system is still a big step. That's what this class is for. This class is here to bridge the gap from the rest of the Pwn.college material into basically stepping into a real role of finding real bugs in real software. And then reasoning about them, exploiting them, reasoning about the effects and what might be done to fix them, and so on. All right. With any luck, all of this will work out great, and you will all go forth and find and cause to be fixed many, many bugs in XNU and other complex targets, because now, after having found bugs and analyzed and reasoned about one of the most important targets out there, the kernel underpinning iOS and macOS and all this fun stuff, you'll be like, whatever, everything else, Linux, child's play. Maybe you can fix whatever the fuck happened to my stupid laptop. Sorry, that wasn't Adam Dupay speaking. That was a bit of yawn coming out. All right, so how will the class work? You notice we have one weekly meeting. That is a long meeting. Today is not going to be long. For one, I have to run, and Rob has been kind enough to take on the load of teaching the very first refresher / hyper fast crash course into ARM. We'll get to that soon. In the weekly meetings, we're going to do whatever we need to do. Sometimes we'll do lectures. Sometimes we'll have discussions about XNU subsystems, about parts of the vulnerability research process, right? As the coolest professor at ASU, Adam Dupay has spent a whole sabbatical year finding bugs in XNU. This is an actual thing you can do, and you can make a living doing this. And we'll discuss that experience, lessons learned there. We'll read code. We'll spelunk through actual kernel code to try to understand bugs and dig into them and so on. Awesome. Okay, we'll also have a bunch of assignments on Pwn.college. How many have done assignments on Pwn.college? Okay. Has anyone not used Pwn.college? Okay. We will, let me just show you real quick Pwn.college. Let's see how we're doing on time. Doing great. Yes. Okay, Pwn.college is already up. Boom. Go to https://pwn.college. A lot of really cool cybersecurity material. A lot of really cool cybersecurity material. All of our class is going to live in here, in the courses section, and in the very most advanced course, because of course, the coolest cybersecurity professor at ASU teaches the most advanced course, except for Rob's course, but it's fine. All right, so right now there's one assignment live. It's the introduction to ARM. So it's already live. I don't know when it's due. Actually, you can find out when it's due. You click in. You can see it's due in 7 days, 7 hours, and 17 minutes. That's a lie. That's a lie?
They'll see it at 8 p.m.
Wait, what? Oh, my bad. This assignment will launch at 8 p.m. There's an administrator logged in, so we can see it. It's fine. Anyways, first assignment launches tonight on Pwn.college. Yeah, here it's hidden. You can see this because you're the dojo's administrator. Great, but you should be able to see the module itself. It doesn't matter. Go to this thing. It's great. All right, one extremely important thing. Extremely important for the 3 people that haven't done course on Pwn.college. Go in here. You click on this course thing. You click on setup. All right, there should also be a link from the syllabus. Make sure that you have 5 green check marks here. This, Rob only has 1. He will fail this course. If you don't have 5 green check marks, you will fail the course. The hardest thing about this course is getting these 5 green check marks. To get the 5 green check marks, you have to create a Pwn.college account, you have to create a Discord, you have to link the Pwn.college in the Discord account, you have to join the thing, blah, blah, put your student ID, it does everything. All right. your grades are going to be available right here under grades. Unfortunately, Rod's failing the course right now. These will be auto-synced to Canvas, maybe? No? Is there Canvas for this course? Okay, fuck Canvas. Again, that wasn't Adam saying that. This will not be synced to Canvas then. Forget about Canvas. Good. So that's your grade. And then you're basically good to go. 5 check marks. Very important. Don't look at that picture. It's outdated. Okay. What else? I guess we won't spend everyone's time. I'll just show how to launch. I'll show where to go to learn how to use Pwn.college. If you go to the homepage of Pwn.college and you go here, getting started. Hey guys, please don't come in late. I, Adam Dupay, get upset when this happens. No, I'm just kidding. Adam Dupay does not mind. Okay, you can click getting started and go through this to learn how to use the dojo. All right, there's 22 people learning how to use the dojo right this moment. Just a couple of nice and easy challenges. You will go through, let's say you want to learn how to use the GUI desktop. You hit start, it loads, starting up a container in the background. Right now it's the first week of school. There's a lot of people. All right. And we say, okay, we're going to connect to our container using the GUI desktop. It loads more. Here's the GUI desktop loading up. A lot of loading so far. That's okay. No problem. Just waiting. Rob might SSH in and kill some containers too.
From my laptop that you're on?
Just kidding. All right, here we go. All right, we spit up a terminal and boom, for this intro challenge, it just automatically gives us a flag. Everything is flag based. All the grades rely on your flags. You copy this flag. You copy it. Oh no, oh no, oh no. Rob, what's happening? Okay. Anyways, we would submit the flag here and everything would be good. Yeah, I'm terrified you have Discord running in the background because I can square.
You got problems.
All right, anyways. It's okay. We're going to hope no one pops up sensitive notifications. Oh, look at that. All right, perfect. So let's come back to the desktop just to show how to copy something out. I don't even know how. So we copied this inside the container. There's this little caret. If you very carefully click on the caret, click here. What the fuck? Again, that wasn't Adam Dupay saying that, even though I'm, okay. So copy. Oh, no, it's, okay, that's copy, okay. Then we go, here it is, copy it out of this text box, bring up this really cool interface, paste this in, I'd hit submit, it would give me the point, and then I could go on to the next level. And it goes to the next level, and we're all good to go. Okay, great. That's how you solve these challenges. Go do the getting started, and then go do the assignment that will launch at 8 p.m. All communication in this course will be on Discord. If you go through and get the 5 check boxes in the course setup, you will end up in the right Discord channels. If you don't, you will fail the class. All right, awesome. Now, grading. I mentioned all the grades depend on solving these challenges. To pass this class, you will learn to find bugs in and exploit XNU. Real XNU on as real of a setting as we can get it and still make it scalable for you guys to tackle. There's also some extra credit. You can get up to 5% extra credit by being helpful to others on Discord. That also includes people in other Pwn.college classes. You're helpful on Discord, people thank you, There's a whole like little right-click app, thank you sort of interface. We'll record that and synchronize extra credit, up to 5% using a logarithmic formula that's very fancy. But basically, help people and you'll get extra credit. And then every week you can get 0.5% by posting good memes that one of the meme judges like in the meme channel. Please, good memes. Shouldn't have to tell you all, you're all very experienced students. Don't post low-effort memes. There's also the meme jail. If you post a low-effort meme, I might put you in meme jail. You will be barred from posting memes for the rest of the semester or until there's a jailbreak. Okay, anyways. Prerequisite knowledge for this class. This class is the second hardest class at ASU. Hardest class at ASU so far demonstrably is Rob's class, who will take over and really pummel you guys today. This is probably the second hardest class. Maybe it'll take the throne and become the hardest class. We expect you to come in knowing everything on Pwn.college. That list basically has everything on Pwn.college. We expect you to know x86-64 and to be able to reverse engineer x86-64. It lost track of me. Come on. There we go. All right. We expect you to know how to write shellcode, writing and reading C, debugging OS kernels, all of this stuff. We'll post these slides on the course in the Pwn.college dojo. We expect a lot. You can learn a lot of this stuff. For example, on Pwn.college, you can do it very rapidly. We don't have a skill check module, so we're going to trust your self-assessment that you're going to be able to survive this course. I think you can all rise to the challenge. Some of you might fail along the way, but that is a price I'm willing to pay. All right. Anyways, no, I'm just kidding. That also, not an official Adam-ism. Okay. Let's see. Everything in this course, we're building live as we deliver. This is the first iteration of the XNU version of advanced vulnerability, applied vulnerability research. Why is this thing insist on losing track of me? This might change. We might find that, hey, we actually can't support actually running the real XNU allocator in Pwn.college, in ARM. We might have to switch it to x86 or something, right? Who knows what'll happen. We'll do our best. It'll be analogous to the very first run of a Pwn.college course ever. The first run of 466 in 2018, where there was a kernel attempt to launch kernel modules where I was loading them onto my laptop that I was presenting from, and then interacting with my buggy kernel module and killing my own laptop and killing the presentation. So anything could happen. It's going to be fun. We're going to learn a lot about XNU security, and we make it work. All right. Now that I, Adam Dupé, the coolest cybersecurity professor at ASU, remember, this will be on a test. You'll actually have to answer who's the coolest cybersecurity professor at ASU. Who is it? Is Twitch with us? All right. Well, let's see. We'll wait for Twitch. All right. You'll have to answer that. Don't forget. I'm gonna bail now that I've scared everyone. I unfortunately have a thing today. It's a crazy week. Yes.
Real quick. So on the syllabus, you don't have a office hours set yet. Will you have office hours?
I don't know.
Okay.
Well, ask next week me. I think so. Yes. I have to admit, guys, I'm not really Adam Dupé, but Adam Dupé will be back next week. But you can tell him that you like the previous Adam Dupé better. I think usually these classes have like the lecture and the office hours, but this lecture is 3 hours long, the lecture period, so it's possible that we'll combine it this time. Cool. Any other questions? All right. Who's the coolest cybersecurity professor at ASU? All right, good. They learned something already. Okay, perfect. I will leave you in the very capable hands of Rob Waz, who will teach you about the jump that you're about to take from the good and right and proper x86 that you know and love as the one true architecture, and go into the dark, evil realm of ARM, where everything is wrong. Rob?
Let's see if we got it here. See?
Follow?
I think we're there.
All right, good luck.
All right.
God have mercy on your souls.
Thank you, Adam Dupay. So, who has seen Whose Slide Is It Anyway? At DEF CON. It's an event they do where you get a random slide deck and you have to present not knowing what it is that you're going to have. That's basically what's going to happen right now, because the 30 minutes that Jan talked was my 30 minutes I was going to look at the slides. So we're going to see what we got and roll with it. Okay? Just out of curiosity, who here has any experience with ARM64? Anyone? All right, we got some hand waving. All right, I'll take it. Please correct me if I start stumbling in the wrong direction, because that is very likely to occur. So let's see what we got here. This is a diagram of a CPU. We've probably seen this diagram of a CPU before. It's a pretty popular one. It has a lot of parts. There's stuff going on. All right, it's going to be very similar to what you already know. Assembly is the only true programming language as far as talking about CPUs, except if you've taken CSE598 or CSE598, the software exploitation class that I teach, where we kind of delve into microarchitectural exploitation, and you learn that assembly is also kind of a lie. But for the purposes of this class, I don't think we're going to go that deep, so assembly will be our ground truth. What kind of things do we do in assembly? Assembly is kind of a very simple language. So we do things such as data manipulation, comparisons, we have control flow instructions, and we can perform syscalls, right? If you know x86, you've probably seen all this. Assembly language has this concept of registers. This is where data is stored. We can also interact with memory. Memory could be the instructions that are being executed that consists of the program. We could be interacting with the stack or some other region of memory that happens to be mapped. So registers exist on the CPU, and they're very fast temporary stores of data. Registers serve as kind of a general purpose storage. Most registers, they don't have an assigned meaning. And this concept goes all the way back to the very first kind of CPUs where we had the 8085. These registers were very small, and we'll notice kind of a consistent naming mechanism in the Intel kind of history of CPUs. Where originally we had, A, C, D, E. When we went to the 8086 architecture, these registers were a little bit bigger. All of a sudden it's AX, CX, DX, BX. We got to x86, which is a 32-bit architecture. This is where some of these registers may be something that you are a bit more familiar with now. We had EAX, ECX, EDX, and then we see ESP and EVP. These are not general purpose registers, right? Does anyone know what ESP or EVP is by chance? Just hit me. I like interaction. What do we got? Stack pointer and base pointer. That is, in fact, what the kind of acronym stands for. In Intel's infinite wisdom, EVP is technically a frame pointer, which I think is kind of funny. But yes, based upon the acronym, that is correct. And then we get to AMD 64, which is the architecture that Jan truly loves, and is definitely what the vast majority of Pwn.college has been. That's where we see these 64-bit versions of these registers, RAX, RCX, RDX, etc. And now we're kind of at what most modern computing is. Now, for this class, as Jan mentioned, we're going to try and do everything on ARM. And ARM is a very different instruction set. And so our general purpose registers are X0, X1, X2, X3, they're just X and then a number. They're all just general purpose registers. Now there is kind of a gotcha there that we'll see if it's on the slides. We'll find out. It is worth noting that on AMD 64, you are used to having EIP or RIP, which is your instruction pointer. On ARM, you actually can't directly interact with RIP, the equivalent or the instruction pointer. Cool. In AMD 64, as you're probably familiar, RAX is the 64-bit register. You can access a subsection of that with EAX, and then a smaller subsection with AX, and then a smaller subsection with AL. You can address partial registers. There's a similar phenomenon here with ARM. The difference here is we have XN, which is going to be your 64-bit register, and then we have WN, which is a 32-bit register. So we just have two sizes here. ARM is a reduced instruction set, so it does have some things that we probably aren't familiar with, or that we can't really map well to AMD 64. One of these things is the concept of a zero register. This is a register that just always has zero. Anytime we move something from it, you're going to get zero. Writing to it is essentially a not, but it exists. ARM has 4 stack pointers, which I didn't know, because I haven't interacted with different privilege levels on ARM. So that will be something exciting to see. ARM also has a link register and frame pointer. The link register is, so in AMD 64, when you perform a call, you push the saved return address onto the stack. The link register on ARM holds that saved return address when the equivalent instruction is executed. Hopefully that's mentioned a bit more later in the slides. If not, we'll try and live demo it and see what happens. I don't care about V registers. All right, nobody wants to deal with SIMD. So how do ARM instructions work? So in x86, we typically have this pattern of opcode, destination, source. With ARM, we have opcode, operand, 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 operand. Like it just, you have a various number of operands. So here we see move follows kind of that similar pattern. We could have move x0, x2. Add, we have add x0, x0, and then #1. Now there actually is, we'll find out, but I believe, a 2-operand version of add. And the 3-version operand of add is specifying where the destination is. So add x0, x01 is the equivalent to add x01. But if for some reason we wanted to add 2 registers and store it in a 3rd register, we have the ability to do that by specifying 3 operands. Similarly, we have things that you've seen before, things like compare and then branch. Now, branch here, B for branch, is the equivalent of a x86 jump instruction. So, sneak a peek. Does he go there? I don't know. I'm going to hit it earlier. So, jump is B for branch. Call, which is where I mentioned, hey, this link register exists. Call, the equivalent on ARM, is BL, which is an acronym for branch and link. So that is saying, hey, we're going to jump somewhere, but we're also going to put a value in that link register so that we have somewhere to return to. Yes?
Maybe I'm just confused, but what exactly is the PC?
Where am I? What is the...
in the link register.
What is the link register?
No,
Oh, PC?
Yeah.
PC, so that is, I believe the acronym there is program counter, which is just another term for the instruction pointer.
So basically the ARM, the ARM equivalent of ARM.
PC is the ARM equivalent of RIP. I believe you can even use PC in like GDB on x86. It's a generic term for the instruction pointer. And we see here that this link register is used on BL, which is the equivalent of the x86 call. And then when we ret, what's really happening is we are setting RIP to whatever is stored in LR. Cool? All right. Why do we have operand, 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 operand? I don't know. I don't know why. But one of the nice things about ARM is that every instruction is 32 bits in size. And this is something that's actually kind of cool once you get used to it, because you can reason and interpret instructions a lot easier. So on x86, for instance, like most push instructions are only 2 bytes in length. But if you wanted to move a 32-bit constant, that's going to be 32 bytes plus something else. So the length of an individual assembly instruction will vary on x86, but on ARM, every instruction is a fixed length of 32 bits. Now, that sounds really cool, but then when you start thinking about it, there's a reason that AMD 64 has these variable length instructions. Right? I said if I have AMD 64 and I want to move a 32-bit constant, well, that 32-bit constant has to be in the instruction. If my instructions are limited to 32 bits in length, how do I move a 32-bit constant? Turns out you can't. Right? That's a problem, because the number I want to move is larger than my limitation on the instruction length. And because of that, ARM 64 has some interesting mechanics that hopefully are included in the later slides. All right, so here we have kind of a loose equivalency between ARM 64 and AMD 64 here. So if we're going to, for instance, move RBX and RAX, the equivalent instruction is going to be move X0, X1. If we want to dereference a memory address, we follow a similar pattern to kind of what we've already seen. We have that move on AMD 64, we have that move RAX and then the brackets RBX plus 4. The equivalent on ARM is we move X0, we still have the brackets, but note that the constant, anytime I'm referencing a constant, it starts with that hash symbol. So we still have that same general kind of pattern that you've seen. Over here, add, we talked about that. Mul. So what do you think mul X5, X6, X7 does? Just based on what I've already said. We got 3 opcodes. What do we got?
Multiplies value in 6 by the value in 7 and put it inside of the spot.
Okay, so the statement for Twitch is we're going to take X6 and X7, we're going to multiply them, and we're going to put the result in X5. Sounds good to me, right? We got 3 opcodes. All right, this makes sense already, and I haven't really done anything. This is good. If you made that logical leap, you might be in the right room. Okay, add X0, X0, hash X1. Any takers? What are we doing? Come on, you right there. What are we doing?
You're adding 1 to X0 and storing the result into X0.
All right, that's beautiful. So the answer is we're taking the value in X0, adding the constant 1 to it, and storing it in X0. Now, we have a few kind of acronyms that are a little bit different, but they're pretty easy to pick up. So right here, I see LDR X0, and then we are kind of dereferencing X1. LDR is a shorthand acronym here for load register. So we're going to load something from memory. We're going to store it in the register. We are loading from loading from the memory address defined in X1. We are storing it in the register X0. Now, what do you think STR is based on what I just said? Oh, we got store register. We are doing good, guys. We're on it, just crushing it. All right, now this one's a trick. What's STP? What do you think? Okay, we got store pointer. That would make, like, I would guess that if I didn't know better. What was, I heard something else. Something about stack pointer. Okay, those letters make sense. I'd take that. We got one more. Okay, now that is a weird thing to say for Twitch here.
It stands for store pair. So.
Yeah. All right, something tells me you've messed around with ARM before. So the statement here for the stream is STP is an acronym for store pair. This is something that we don't have an equivalent really at all on AMD 64. And so we're storing, so we're taking the pair of registers, X1 and X2, which are how big in size? Well, I heard a few things. What do we got? All right, so one of the statements was 32 bits. The other one was 64 bits. So The X registers are 64 bits. The W registers are accessing the lower 32 bits. So when we have store pair X1, X2, we are actually storing two 64-bit registers to the memory location that is defined in X0. So this is one instruction that is moving 128 bits. We're putting two registers worth of data to memory in one instruction. So things definitely get a little bit weird, and they can get weirder depending on what's in the next slide. Okay, well that isn't that weird. Come on, we can do better than that. Here we see that you can access smaller amounts of data in a register. We have the same phenomenon here in AMD 64. So we can, for instance, load an individual byte, a half word, a word. I don't think that's particularly interesting, but you see how we can suffix these instructions to pull that off. I don't know what BFI is. Oh, the slide says it. It says instructions can move and manipulate bits from one register to another. A bit field insert. Okay, all right, Adam. Let's see what we got here. BFI X1, X0, 9, 6. So I've got 4 operands. We're going to move the lower 6 bits into X1. Where bit 9 in X1 is the lowest. What? Anyone translate this for me? All right. We got a guess? We don't got a guess. All right. So what happens if we don't know something? Like, what's your general strategy? If you've made it this far in cybersecurity, you're probably not being in the unknown is not not foreign to you. So what should we do? All right, we're parsing the slide. Stack Overflow. Okay, that's pretty good. That's pretty good. If this were a different topic, I would have said read the man page, right? But we don't have man pages here. But one of the things that is hiding at the bottom of these slides, boom, is the ARM documentation, which used to be linked in the Pwn.college dojo, and then ARM changed the web address, so now it doesn't go here. It's actually very solid documentation. Let's see if I can find the right one. And we can take a look here. What am I looking for? BFI. Bit field insert, which apparently is an alias for BFM. Did he have that there? Did he get us BFM? No. See, Adam's showing us this alias. All right, documentation is truth. BFM. What do we got here? Oh, now it just says it's always accessed by its alias. Then why have the real instruction? Okay, so it's copying a subset of the register from A, B. All right, I'll take it. Instruction visualization. Oh, I should have just gone to the next slide. All right, let's learn together here. What do we got? So I got BFI, X1, X0, 9, 6. Where does 9 fit in here? Where does 6 fit in here? Okay. BFI. Oh, he's going for a W now, so we're a different register. 9, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. 1, 2, 3, 4, 5, 6. All right, these numbers kind of make sense. So we are grabbing from this first register, and we are moving it into an offset and then a length into it that we're copying. Did ARM man, did you know it? Okay, you didn't know it either. All right, I feel a little bit better. All right. What do we got here? UB. What are you doing here? What is this shenanigans? All right. UBFX. Move 7 bits in X1 starting from the 18th. Lowest bit to the lowest bit in X0. Okay, that's like functionally the same thing, isn't it? Yes, because we're going 18 deep, we're grabbing 7, and we're throwing it here at the beginning. Okay, so they're inverse operations. In the first one here, we are grabbing from the beginning of the source, and then we're defining the offset and the destination. And then here, if we look at UBFX, we are setting the offset in the source, and then putting it at the beginning of the destination. All right, we got there. I'll take it. All right. Why does this thing grab 0? This last one here. We got BFI W1 WZR34. Where do these zeros come from? It's a trick question. Not really. Zero register. Yeah. So WZR, calling back to the earlier slides, is our 0 register. So we are copying something from the beginning of the 0 register, which is all zeros. We're defining the offset, which allows us to 0 a certain number of bits in our destination register. Okay, so there are no push or pop instructions on ARM64. That kind of sucks. Like, let's be real here. Instead, we have this concept of pre-indexing and post-indexing. We have this concept of like accessing a value while simultaneously incrementing it or decrementing it. And we can increment or decrement it before the access or increment or decrement it after the access, which is hopefully what we have showing here. Okay, we do have it. I have to consult my handy notes here to make sure I get this right because I don't want to say it wrong on stream. So here we have store register. We're going to store the value that is in register X4 to the stack pointer minus 8 bytes. Well, what is this exclamation point doing?
It's first gonna decrement it and then.
Okay, so the comment for Twitch is we're going to first perform this subtraction. This is a pre-index. So we are storing this at the stack pointer minus 8 because we have this exclamation point. Here we have store pair. So we are storing 16 bytes. We have the exclamation point, so this is a pre-index. We are storing this pair at the stack pointer minus, I can't math, 128 bits, 16 bytes. So it's the equivalent of doing 2 pushes in one instruction. Kind of pulling over from AMD 64. All right, this one right here does not have the exclamation point. We have a different syntax. So we have load pair x0, x1. We're accessing the stack pointer, and then we have a comma and a constant. This is a post index. So we are pulling this from the stack pointer and then performing the addition. It's the equivalent of doing 2 pops, which is what we have over here. Similarly, this is a post index, so we're going to grab the value at the stack pointer, throw it in X4, and then add to the stack pointer, so it's the equivalent of a single pop. But we have to be aware of this post index, pre-index notation. All right, branching. Branching, honestly, I think is kind of easier to understand on ARM than AMD 64 because we just have B for branch, and then you have this conditional kind of suffix. So it's B dot, and then what are you looking at? I don't care about that. Conditional select. All right. ARM man, you got me? No? It's all right. It's all right. We can just go to the documentation, man.
It's true, I guess it will take the first, second operand and put it in the destination.
Okay, yeah. If we actually just parse the logic of the slides, we might get there. The logic of the slides here says that we are setting XD to either XN or XM based upon condition. Yeah, Adam went deep into ARM on this one, man. Syscalls. We don't have a syscall instruction. We have a service instruction. The rest of them, I don't know, man. Adam's going to have to save you there. The syscall number, which traditionally on AMD 64 is going to be an X8, on AMD 64 would be an RAX. On ARM is going to be an X8. A calling convention for the syscall on AMD 64, you're used to RDI, RSI, RDX, blah, blah, blah. ARM actually kind of makes it kind of easy. We just start counting from 0 up. Those are your arguments. After this, I believe after X7, they end up on the stack. So we don't actually fill every general purpose register. Oh, what do you know? We got there. So, calling conventions. As I mentioned, calling a function is BL for branch and link. The return address, instead of being pushed to the stack, is stored in this link register. If you have something in the link register and you branch again, it does end up on the stack, the prior return address from the earlier function frames. Calling conventions, callee saved. That's fine. Cool. Did I make it to the end? We made it to the end. All right. How long does this class go? One of the things I don't think, I'm just going to throw it out there. There is no textbook for the class, but I will say that this book is loosely going to be kind of referred to or used as a reference for how the class works. Not required. It is a hard book to acquire. You can't just like order it on Amazon as like a normal bookstore thing. There's like one seller and it's the author. The book itself is several years out of date. There's several versions. So there's the Star OS and then there's slightly different name that's an older version. Both of them are old enough to where a lot of the implementation details that are described there as far as Mac OS aren't necessarily accurate. But the general feel of it, if you parse it and then just try stuff, you can figure stuff out as you go. Getting that information is actually very hard. There's not a lot of public information on how those mechanisms work. All right. The next question is, did what I was installing work while Jan was lecturing? All right, here's our big gamble. Does anyone have any questions for me before I just bomb a demo? Damn. All right. Yeah, I was hoping you guys would save me. All right. In theory here, what I have is a Docker environment that's running on ARM, which means we should be able to use some familiar Pwn tools things to kind of just compile and run some ARM assembly. So from Pwn import star. Oh, I did install GDB. So let's see if that works. Oh no, I know GDB doesn't work. The demo is ruined, guys. Specifically on Mac, if you're using Docker's random factoid, if you're using Rosetta on a Mac to use GDB, there's like some special magic you have to do, and I did not do said magic. I don't remember the magic. All right, guys. So that is, I suppose, all I can hit you with. One of the first assignment, as Jan mentioned, is live at 8 o'clock, although honestly you can access it right here, not under your dojos, but it's going, as far as I'm aware, it's the exact same challenges that are on the community ARM dojo. It does specifically try and make you utilize some of these odd instructions. It is meant to be educational. It's not like a giant, hey, get punked. And so if we use the dojo instead of my amazing GDB demo that failed, I'm going to use SSH to connect to it. Hopefully the dojo's not on fire. We'll find out. Beautiful. So these challenges start off very simple. It's just, hey, let's set a register. Hopefully you can do that. We're going to move x1 and then a constant where we start with the hash. As you get to the later challenges, it's going to start putting restrictions on you where you can only use specific instructions, or we're going to limit the number of instructions. And so now you're going to have to start using some of these, for instance, storing pairs, loading pairs. You're going to have to deal with that post-index, pre-index to optimize your assembly so that something that you could write in, say, 10 instructions, you're now going to have to do in like 4. In general, ARM has a small number of instructions, but a single instruction will do a lot of things, depending upon how you structure it. Which makes it kind of cool. This dojo is designed to hopefully make you utilize some of those concepts. With that, I got nothing. If you got nothing, we're gonna call it. I'll check Twitch and see if my favorite troll has hit me. I think they're sleeping. Yeah, the troll is sleeping. Somebody says on Twitch, what is the path on Pwn.college that I need to follow to get the requirements for this course, CSE598? So that's a fair general question. So Pwn.college as a site in general is open to everyone. If we go to dojos here, you see this progression of orange, yellow, green, blue. This course is not in anywhere currently in this progression, but it would be equivalent to this blue belt level. As far as the expectations. So if you wanted to have the requisite knowledge, you would want to go through orange, yellow, and green. For a little bit of perspective, that's roughly 2 semesters worth of university education at the 300 and 400 level here at ASU as far as what the general expectations going in are. So to start the orange belt, it's kind of assuming you have a couple years of general computer science under your belt. If there's nothing else on Twitch, which I don't believe there is, we're going to wrap up there. I appreciate everyone hanging out. Next week should be the real Adam.